talk about evolution, I mean evolution since day one, since the Big Bang. My idea of evolution is based on the principle of least action. But by the way, my name is Javier de Rivero Paredes, and that's me in my 20s, and now in my 60s, and I call that the evolution. I have held several degrees and classes in physics, biology, but I am not a physicist, a biologist, or a chemist. A great biologist, Theodore Loshansky, has said, nothing in biology makes sense except in the light of evolution. Since the Middle Ages, we know the laws that govern physics and chemistry in unanimated nature also govern life biology. Does God play dice with the universe? Well, maybe. In physics, we have the principle of least action, or stationary principle. This universal principle establishes that matter does not follow a random path, but a minimizing or stationary path. It chooses a path. Nature chooses a path. Like Coppersmith title of his book, The Lazy Universe, an introduction of the principle of least action. He's pointing that the universe is lazy. Now that we know that, nature doesn't follow a random path, but a minimizing or stationary path, how can proteins, amino acids, the formation of amino acids and proteins biochemical processes are random? How can that be possible? Natural selection Darwinian or neo-Darwinian theories try to explain the animate world as a living entity where mutations are random. However, the last few years there have been some papers that try to prove the fact that mutations are not random in evolution. We have this energy. It's a very important concept in chemistry reaction. Free Gibbs is thermodynamically available energy can be formulated in terms of the principle of least action. We can see this better in this evolution timeline. The universe was formed 13 to 15 billion years ago, the first inorganic elements. And later, much later, we don't know when, amino acids were formed. Later, proteins. They were random? I don't think so. And much, much later, 1.5 to 3.5 billion years ago, the multicellular organisms show up, and that's when we can say life started, and we can say Darwinian or neo-Darwinian theories start to work. But the principle of least action was still there, is still there. I am going to make a brief history of the principle of least action. Heron of Alexandria, about 2,000 years ago, studying light, he discovered that light follows a minimum distance. The path of the light is minimum, and he called that the principle of least distance. 1600 years later, in 1657, Pierre de Fermat, also studying light, he studied refraction from reflection. He said, no, light doesn't follow a minimum distance, but follow a minimum time. And he called that the principle of least time. By about 100 years later, Joseph Louis Lagrange and Maupertuis found that this minimizing principle doesn't apply only to light, but all matter in the universe. Lagrange did which is called today the Lagrangian, which is the difference between kinetics and potential energy, and called this difference the action. He found that the matter minimized this difference, minimized the action. Later, in 1834, Hamilton found that this action is not a minimum, is the minimum or maximum, and he called that the stationary action.
Now we are in the 1900s with Einstein and the theory of relativity. Does the principle of Lip's action give the same results? The theory of relativity? Yes, it does. But a small difference can be found in the orbit of Mercury. Using exactly the same formula, kinetics minus potential energy. And later, in 1942, Richard Feynman, in his PhD thesis, he proved that the principle of this action gives the same result also in quantum mechanics, following the path integral, Riemann path integral, which is a quantum analog of the principle of this action. As I said before, thermodynamics can be put in terms of the theory of this action based on Lagrange motion. The state of the system, the force of the state of the system, potential and kinetic energy and difference drive the system toward a more probable state via flows of energy that diminish the difference. In terms of proteins, there is the so-called thermodynamic hypothesis, other times called Amphisem's dogma. Means that the native state, the working state of a protein, should be the global minimum of free energy. And now I am going to show you the delta G, which I talked about before, the Gibbs free energy. That formula that William Gibbs put the first and second law of thermodynamics in one formula. And that delta G is equal to the enthalpy minus T, the temperature, multiplied by the entropy. And that has to be negative for a reaction to be spontaneous. In this case, the reaction is called exergonic. And one reaction that is with the delta H enthalpy is called exothermic. So it's ideal to have an exergonic and exothermic reaction in a chemical reaction. Now, after seeing the thermodynamics of the reaction, we are going to see the kinetics of the reaction. As I said before, delta G, if it's negative, it's a spontaneous reaction. But we have to account for the reaction time, the reaction speed. A slow reaction can take millions of years, even maybe billions. Then we need to find two amino acids that have a reasonable amount of time in the reaction. And the two factors that affect the speed of the reaction is the temperature and activation energy. The temperature, according to Arrhenius' formula, a higher temperature gives you higher speed, as well as a lower E sub A, which is the activation energy, gives you also higher speed. We can see that better in the Maxwell distribution, the chart to the left. In the chart to the left, we can see two curves. The curve to the left is the curve with lower temperature and lower speed. The curve to the right, red one, is a higher temperature, more particles are going to be a higher speed. The same thing we can see that chart to the right, the activation energy. A lower activation energy, which is the lower curve, is going to be better to complete the reaction in a reasonable amount of time. Then we need amino acids in the universe. But as Stephen Fry has said, the universe seems to love amino acids. And we have amino acids in extraterrestrial meteorites. And our body has amino acids. But what happens in our body? The chemical reaction between amino acids, the delta that G gives, free energy is positive, non-spontaneous and favorable. Thermodynamically unstable but kinetically stable. And we also have a complex molecule like ATP produced by the mitochondria. And that molecule adds that extra energy when amino acids combine to form proteins. But what about early dipeptides in the prebiotic soup? We have found the early dipeptides, and we found those two amino acids that can form a dipeptide spontaneously. Yes, we have them. We have found them in extraterrestrial meteorites. And those are glycine and proline, probably the earliest amino acids in the prebiotic soup. In the next study, we are going to see, this is a study by Jetting Blue in 2021, cyclic dipeptide formation from linear dipeptides, experimentally proved that two amino acids can be formed with delta G negative and delta H negative. That means an exothermic and exergonic reaction. No need of ATP. And they use an alkaline aqueous solution 3-metaphosphate, P3M. And they found that the delta G is around -609, and almost the same as the delta H, both of them negative. That means that this is a spontaneous process at any temperature, with, of course, the delta, the S, which is entropy favorable. I have to point out that the reaction between glycine and proline is not the same with proline and glycine. The product is the same, but the reaction is different. What I mean, we are going to see in the next slide why it's different. Which combination is better? In the next slide, I am going to show you the kinetics of the reaction. How can the combination of glycine and proline is different than the linear proline and glycine, other matters. And the reaction linear glycine and proline has a 33.2 kilojoules as the E sub A, or transition energy or core energy activation. Is lower than the proline and linear proline and glycine. The linear proline and glycine, according to the study, they couldn't find the activation energy. It was so high that it was impossible to measure. But the other one, glycine and proline, was good, was okay. They measured. According to Arrhenius' formula, as we saw before, a lower activation energy is favorable for the kinetics of the reaction. I performed a computer simulation using Avogadro and Orca with the two amino acids that we found in this study that have delta G negative, that means a spontaneous reaction. My results were similar qualitatively than the result of getting WHO in 2021. I found that the delta G is negative, the same as the delta H. Both of them are negative. That means it's a spontaneous, exergonic, and exothermic reaction. The results I found were about minus 684.51 for the delta H and minus 684.57 for delta G. Both of them are with a 12% margin of error. In the next slide, I will show you how the mutations are not random. I will list two studies. The first study was a plant study by J. Mongo, Natural Selection in Arabidopsis thaliana from 2022. After observing thousands of mutations, they found that the mutations were not random. There was a paradigm. The mutation is a force of evolution, and the mutations were in the direction of beneficial mutations, something against the Darwinian or even neo-Darwinian theories, more like Lamarckian or neo-Lamarckian. Well, in the second study they studied the human hemoglobin by Daniel Melamed in 2022. They found that the data suggests a structure of mutation rates involving mutation-specific influence. The mutations were in this study originated in different regions, geographical regions, and that was also a bias in the mutation. These two studies don't mention the principle of least action, but they have a directionality. Mutations are not random, and the directionality may be due to different factors. One of them might be the principle of least action. Now, have we found amino acids in meteorites, in extraterrestrial meteorites? Yes, we have found them. They are not rare in the universe. And they are similar to the amino acids found on Earth, and are, according to some authors, the basic amino acids that form the early life in the universe, including glycine and proline, that was a matter of the study of getting WHO and my simulation. Although individual amino acids have been found in abundance, there have been only 2 reports of polymers amino acids. And these polyamino acids have been found in the Allende carbonaceous chondrite meteorite. In this table, the motion from meteorite 1969, that's 19, has 86 amino acids. And 10 of those 86 amino acids are part of our 20 amino acids that form proteins. As I said before, including glycine and proline. Even some of those amino acids we don't know. We don't have those amino acids. We're totally new. This meteorite, as I said, fell in 1969. By the way, the data of this slide is from an article, a new family of extraterrestrial amino acids in the Murchison meteorite by Toshiki Kogas and Hiroshi Naraoka from 2017. Amino acids in the universe, the probability of formation are very low. And now I am going to end with a conclusion, with my conclusions. As I said before, if processes in physics and chemistry are not random, how can mutations, formation of amino acids, and proteins, which are biochemical process random, if presentation start with the existence of amino acids, because we have found them, found from Earth in carbonaceous meteorites. That is my opinion that the principle of Lewis action also affects the formation of amino acids, the basic one, the one we need for the formation of life. The principle of Lewis action is the closest since to a theory of everything in physics. It works with Newton, Newton, classic mechanics, relativity, and quantum mechanics. God plays dice with the universe, but the dice are loaded. The evolution of the universe has a train, and that train is pointed in the direction of the principle of Lewis. Chances of forming one protein of 150 amino acids, which is an average length, is 1 in 10 to the 164. The probability is so small that not even waiting billions of years, the protein could have been formed by chance. However, we have seen that the peptide can be formed as well formed spontaneously, as well we have found amino acids in meteorites. Some researchers are looking for a missing law in the evolution of the universe, but the principle of this action is almost 2,000 years old and tested. There might be bubbles of quasi-random behavior, and later, with the impact of animate beings, comes natural selection, more than winner or than winner. This action doesn't replace natural selection as we know it, since life starts in animate beings, add more complexity to evolution. It adds one more factor in the evolution of animate beings. It extends the principle of natural selection. And before animate beings, it is a factor that makes amino acids happen and form dipeptides. We cannot compare evolution after animate beings or so-called natural selection, because the principle of Lewis action is working since day one. Thank you. Really thank you, because you have to forgive me. I have an accent in English, and also in my first video on YouTube. But I think the natural selection should be extended to day one in evolution, because this action is part of nature. Thank you.